NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will simplify two radical expressions by following a clean, visual algorithm. First, rewrite every number inside the radical as a prime power, next convert to a common root index where possible, then combine like radicals, and finally simplify any products using least common multiples of the indices. Let's start with an example. We will follow the exact step order shown on screen. Here is the first expression. First, display it. Step 1. Rewrite numbers inside radicals as prime powers of 3. For example, 9 equals 3 squared, 27 equals 3 cubed, and 81 equals 3 to the 4th power. Step 2. Convert the first 3 radicals to a common index of 5. The 10th root of 3 squared becomes the 5th root of 3. The 15th root of 3 cubed also becomes the 5th root of 3. For the product with indices 5 and 20, we will convert the 5th root to a 20th root using the least common multiple of 5 and 20. That is, the 5th root of it equals the 20th root of a to the 4th power. Step 3. Simplify the product of the 20th roots. We multiply inside the same radical. 3 to the 16th times 3 to the 4th equals 3 to the 20th. Step 4. The 20th root of 3 to the 20th is simply 3. So the expression becomes 12 times the 5th root of 3 minus 12 times 3, which is minus 36. Now, we apply the same algorithm to the second expression. Here is the second expression. Step 1. Rewrite everything as powers of 5 inside the radicals. 25 is 5 squared, 125 is 5 cubed, and 625 is 5 to the 4th. Step 2. Convert each radical to a 7th root using the greatest common divisor rule. 14th root of 5 squared becomes 7th root of 5. 21st root of Step 2. Convert each radical to a 7th root using the greatest common divisor rule. 14th root of 5 squared becomes 7th root of 5. 21st root of 5 cubed becomes 7th root of 5. 28th root of 5 to the 4th becomes 7th root of 5. Step 3. All terms are the same radical, the 7th root of 5, so we combine coefficients. 13 minus 5 plus 2 minus 10 equals 0. Summary. We followed the same algorithm twice. Rewrite the radicands as prime powers, convert to a common index using greatest common divisors or least common multiples, then combine like radicals and simplify any products. Our final answers are 12 times the 5th root of 3 minus 36 and 0. Our final answers are 12 times the 5th root of 3 minus 36 and 0. In this lesson, we will simplify two radical expressions step by step following a clear algorithm. Factor the radicand to expose perfect powers. Extract those powers from the root, and then combine like terms. We will simplify these two expressions. First expression, second expression. Part A. Strategy. Rewrite each radicand to expose perfect powers. 54 is 3 squared times 6. 36 under a 4th root is 6 squared. 24 is 2 squared times 6. Now extract the perfect powers. Square root of 3 squared becomes 3. 4th root of 6 squared is the square root of 6. And square root of 2 squared is 2. All terms are multiples of the same radical, square root of 6. Factor it out and combine the coefficients. Evaluate the arithmetic to finish part A. Let's continue to part B. Again, expose perfect powers. 405 is part B. Again, expose perfect powers. 405 is 81 times 5. 25 is 5 squared. 625 is 5 to the 4th. Convert the fractional exponents. 8th root of 5 squared equals the 4th root of 5. 16th root of 5 to the 4th also equals the 4th root of 5. Also, 4th root of 81 times 5 becomes 4th root of 3 to the 4th times 5. Extract the perfect 4th power. 4th root of 3 to the 4th is 3. Now, all terms are the same 4th root of 5. Factor it and add the coefficients. Finish the arithmetic to get the result for part B. Summary. We factor the radicands to reveal perfect powers. Extract those powers from the root, and then combine like radicals. Our final simplified results are -8 times the square root of 6 and 2 times the 4th root of 5. Extract those powers from the root, and then combine like radicals. Our final simplified results are -8 times the square root of 6 and 2 times the fourth root of 5. In this lesson, we will simplify two expressions by factoring perfect powers out of radicals and then combining like terms. Example A. Simplify the expression. Cube root of a to the fourth minus 5 times the cube root of a to the eighth plus 3 times the cube root of a to the 16th minus 2 times the cube root of a to the fourth plus 7 times the cube root of a. Step 1. Split each exponent into a multiple of 3 plus a remainder. That lets us pull perfect cubes out of the radical. A to the fourth is a cubed times a. A to the eighth is a to the sixth times a squared. A to the 16th is a to the 15th times a. Now rewrite the whole expression using those simplified pieces and group like radicals. Combine the like terms that contain cube root of a. The coefficients are 1 minus 2 plus 7, and we also keep the term 3a to the fifth times the same radical. The term with cube root of a squared is not like the others, so it stays separate. Evaluate 1 minus 2 plus 7 to get 6, and then factor out a times cube root of a from the first two terms. Example B. Simplify the expression. The fifth root of a to the sixth b to the sixth minus b times the fifth root of a to the sixth b plus the 10th root of a to the 12th b to the 12th plus 12 times the fifth root of a b to the sixth minus 9 times the 15th root of a to the 18th b to the 18th. Convert every radical to the common building block, fifth root of ab. We use exponent rules to rewrite each piece. The fifth root of a to the sixth b to the sixth equals ab times the fifth root of ab. B times the fifth root of a to the sixth b equals ab times the fifth root of ab. The 10th root of a to the 12th b to the 12th is ab to the power 6/5, which is ab times the a to the 12th b to the 12th is ab to the power 6/5, which is ab times the fifth root of ab. 12 times the fifth root of ab to the sixth equals 12 ab times the fifth root of ab. And the 15th root of a to the 18th b to the 18th is ab to the power 6/5, so 9 ab times the fifth root of ab. Now rewrite the entire expression using that common factor and combine coefficients. Add the coefficients 1 minus 1 plus 1 plus 12 minus 9 to get 4. Summary. When simplifying radicals, split exponents by the index to pull out perfect powers. Rewrite everything with a common radical when possible, and then combine like terms. For example, we obtained a times the cube root of a times the quantity 6 plus 3a to the fourth minus 5 a squared times the cube root of a squared. For example B, we found 4ab times the fifth root of ab. ab times the fifth root of ab. We will fill each square by combining like radicals. Watch the pattern in every line and follow the arithmetic on the coefficients. Problem 1. A square minus square root of 6 equals 5 square root of 6. Move the square root of 6 to the right side. Combine the coefficients. Simplify to get the final value for the square. Problem 2. -2 square root of 7 minus a square equals -3 square root of 7. Add 2 square root of 7 to both sides. Combine the coefficients. Multiply by -1 to isolate the square. Problem 3. The cube root of 2 minus a square equals 2 times the cube root of 2. Move 2 times the cube root of 2 to the left by subtraction. Combine coefficients 1 minus 2. Conclude the value of the square. Summary. The three missing values are 6 times square root of 6, square root of 7, and negative cube root of 2, root of 7, and negative cube root of 2. In this lesson, we will solve two fill-in-the-blank radical equations step by step, following the exact algebraic structure shown. We'll simplify radicals and combine like terms. Example. Start with the equation. Square root of 5 plus square root of 20 plus a blank equals 7 square root of 5. Isolate the blank on the left by subtracting the other terms. Rewrite square root of 20 as square root of 4 times 5. Take the square root of 4 to get 2 square root of 5. Combine like terms. 7 minus 1 minus 2, all times square root of 5. The blank equals 4 square root of 5. Now, the second equation, with cube roots. We begin with cube root of 12 plus cube root of 96 minus a blank equals negative 3 cube root of 12. Move the blank to the right, and move negative 3 cube root of 12 to the left. Rewrite cube root of 96 as cube root of 8 times 12. Simplify the cube root of 8 to get 2. Combine coefficients, 1 plus 2 plus 3. Therefore, the blank equals 6 cube root of 12. To summarize, the first blank is 4 times square root of 5. The second blank is 6 times the cube root of 12. We achieved both by rewriting composite radicands and combining like radical terms. In this lesson, we will solve an infinite nested radical. We want a simple expression for the value of s defined by south equals the square root of a plus the square root of a plus the square root of a, and so on forever, assuming a is positive. The key observation is self-similarity. The part after the first a is the same infinite radical again, so we can label that whole repeating piece as s. Now, we turn the picture into algebra. If south equals that square root expression, then squaring both sides gives s squared equals a plus s. Let's move all terms to one side. We get s squared minus s minus a equals 0. This is a quadratic equation in s. We can solve it using the quadratic formula. So s equals 1 plus or minus the square root of 1 plus 4a, all over 2. Which root should we take? Since a is positive and s is a nested radical, s must be positive. Therefore, we keep the plus sign and discard the negative 1. For intuition, let's try a equals 2. In this example, we will prove an inequality for all real numbers a and b. First, show the word example. Now, display the problem we aim to prove. It reads, the fourth root of a to the 8th plus b to the 8th plus the quantity 8th root of 4 times ab raised to the 4th is less than or equal to a squared plus b squared. Step 1. Simplify the inside sum exactly as follows. Start with a to the 8th plus b to the 8th plus the quantity 8th root of 4 times ab to the 4th. Replace that power by 8th root of 4 to the 4th times a to the 4th b to the 4th. Since 4 to the 4th equals 2 to the 8th, its 8th root is 2. Therefore, we have a to the 8th plus b to the 8th plus 2, a to the 4th b to the 4th. Recognize this as a perfect square, namely a to the 4th plus b to the 4th, all squared. Step 2, take the 4th root of that perfect square. The left side becomes the 4th root of a to the 8th plus b to the 8th plus the quantity 8th root of 4, ab to the 4th equals the 4th root of a to the 4th plus b to the 4th, all squared, which is the square root of a to the 4th plus b to the 4th. Thus, our inequality is the square root of a to the 4th plus b to the 4th is less than or equal to a squared plus b squared. Step 3. Square both sides to remove the square root. We get a to the 4th plus b to the 4th is less than or equal to the square of a squared plus b squared. Expanding the right side gives a to the 4th plus 2 a squared b squared plus b to the 4th. Step 4. Subtract a to the 4th plus b to the 4th from both sides. We obtain 0 is less than or equal to 2 a squared b squared. Since squares are non-negative for all real a and b, the inequality is always true. Therefore, the original statement holds for every real pair a and b. In this lesson, we'll prove a beautiful identity using 2 given conditions. We'll go step by step and keep the algebra very visual. Here are the givens. And here is the statement we want to prove. Step 1. Start from the left-hand side. Rewrite each term so that ax squared becomes ax cubed over x, and similarly for the others. Step 2. Use the equality ax cubed equals by cubed equals cz cubed. Replace each numerator by ax cubed. Then factor out ax cubed. Step 3. Use the second condition that 1 over x plus 1 over y plus 1 over z equals 1. The expression becomes ax cubed times 1. The cube root of ax cubed is x times the cube root of a. By the exact same reasoning, the left-hand side also equals y times the cube root of b and equals z times the cube root of c. Let that common value be lambda. Then the sum of the 3 cube roots equals lambda times the sum of 1 over x, 1 over y, and 1 over z, which is 1. Therefore, the sum of the cube roots equals the original cube root expression, completing the proof. Final statement. Example. We will prove a classic identity built from the golden ratio numbers. First, read the statement we want to show for any natural number n. The claim is, open parenthesis, 1 plus square root of 5 close parenthesis over 2 to the n, plus the same base to the n minus 1, minus the version with 1 minus square root of 5 over 2 to the n, minus that base to the n minus 1, equals the difference of those two bases raised to n plus 1. Step 1. Factor the common power in each pair. From the left pair, factor the base to the n minus 1. From the right pair, factor the other base to the n minus 1 as well. Step 2. Simplify each parenthesis. 1/2 times 1 plus square root of 5 plus 1 becomes 3 plus square root of 5 over 2. Similarly, 1/2 times 1 minus square root of 5 plus 1 becomes 3 minus square root of 5 over 2. Step 3. Recognize a perfect square. 3 plus or minus square root of 5 over 2 equals open parenthesis 1 plus or minus square root of 5 close parenthesis squared divided by 4. Step 4. Move the division by 4 inside the base, which turns each factor into the base 1 plus or minus square root of 5 over 2, all squared. Step 5. Use the law of exponents. The base to the n minus 1 times the same base squared equals the base to the n plus 1. Apply it to both terms to reach the right-hand side. We proved the identity by 4 clean moves. Factor a common power, simplify the parentheses, recognize a perfect square, and finally add exponents. This mirrors the structure shown in the reference solution and works for every natural number n. Example. We are given an equilateral triangle with side length a. Our goal is to find the height h in terms of a and then the area in terms of a. Let's draw an equilateral triangle and drop its altitude. The altitude meets the base at the midpoint, creating a right triangle. We label the slanted sides. Each half of the base are over 2, and the altitude h. Consider the right triangle formed by one side, and the altitude by the Pythagorean theorem. A squared equals over 2 squared plus h squared. Solve for h squared. That is, h squared equals a squared minus a squared over 4, which is 3a squared over 4. Now take the square root to get h equals the square root of 3a squared over 4. That simplifies to square root 3 over 2 times the absolute value of a. Since it is positive, h equals square root 3 over 2 times a. Now compute the area. Area equals 1/2 times base times height. Substituting the base a and the height square root 3 over 2 gives the final area. In this video, we will follow the exact step order shown to evaluate the expression x plus 4 over square root of x, given that x is positive and that x plus 2 times the square root of x equals 2. We'll mirror the written algorithm line by line. Step 1. Start from the given equality. X plus 2 square root x equals 2. Step 2. Factor out square root x on the left. Step 3. Divide both sides by square root x. Step 4. Simplify the left-hand side. This yields square root x plus 2 equals 2 over square root x. Step 5. Multiply both sides by 2. Step 6. Add x to both sides to form the expression we need. Step 7. Substitute the given value x plus 2 square root x equals 2. Step 8. Evaluate the right-hand side. Therefore, x plus 4 over square root x equals 6. We will solve a classic radical equation system in a single clean sequence. First, here is the problem statement. Step 1. Introduce simple variables for the square roots. Let m equal the square root of a minus 19, and n equal the square root of b minus 17. Then a plus b become m squared plus n squared plus 56. Step 2. Substitute m and n into the original equation and simplify. 3m plus 4, n equals 1/2 of a plus b minus 11, which is 1/2 of m squared plus n squared plus 25. Now multiply both sides by 2 to clear the fraction. Step 3. Move all terms to one side and complete the square for m and n. That gives m squared minus 6m plus n squared minus 8n plus 25 equals 0. Add and subtract 9 and 16 to complete the squares. We obtain left paren m minus 3 right paren squared plus left paren n minus 4 right paren squared equals 0. A sum of two squares is 0 only if each square is 0. So m equals 3 and n equals 4. This corresponds to the single point 3, 4 in the m/n plane. Final step. Back substitute to recover a and b. From m equals 3, we have square root of a minus 19 equals 3, so equals 28. From n equals 4, we have square root of b minus 17 equals 4, so b equals 33. Therefore, a plus b equals 61. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.